Hello, my name is Cole Hendricks, and today I will be helping you design climate-specific solar shading devices for Architecture 242. We're going to be looking at a real-world example and understanding how we can create an effective solar shading strategy for this building. We're going to be looking at the Yakitutu dorm Nipumu on the south side of the Cal Poly San Luis Obispo campus. This building is oriented so that it has a long elevation facing south, right here, facing south towards the equator. And we want to create a new solar shading system for this south elevation, shown here. To start, let's get all the charts and data we need to complete this task. To create an effective solar strategy, we need to access first what's called the solar protractor, also known as the shading mask protractor and a shading protractor. For our class, one has been provided. You can also find this tool online and in various versions of the books Introduction to Architectural Science by Stephen Zokole and Mechanical and Electrical Equipment for Buildings by Walter Grunzig and team. Just a little bit about this chart. Here we have the horizontal shadow angle, the HSA in red. That's going to help us determine the shadow angles on a plan drawing. Then we have our VSA, or our vertical shadow angle, which gives the shadow angles on a vertical plane or in a section drawing. Okay. And then here we have our end profile, and we're going to use this on an elevation drawing. It helps us determine the width of our overhang. Okay. So here's a little visual representation of each of these. You can see the HSA is a plan drawing, helps us determine the size of the fin we need, and the VSA is in section, helps us determine the size of the overhang we need. Okay, so remember, HSA is a fin, VSA is an overhang. So this is the first tool we need. The second tool we're going to need is called the 2D Polar Equidistant Coordinate Sun Path Chart, which can be accessed via the University of Oregon and at andrewmarsh.com. Here you can see this is the University of Oregon Solar Radiation Monitoring Laboratory. You put in your latitude and longitude. You can output a chart just like the one I showed you. And here at andrewmarsh.com, you can go to his software and you can find the polar sun chart there. So let's go back to this and let's do a little breakdown of this chart. Here you can see we have the months on this side, and it's important to note here these months are paired together because the angle of the sun will be the same for these 2 months. So in August and April, the angle of the sun is the same. Okay. Here along this line we have our times, so that ranges from 6 a.m. all the way till 7 p.m. And then lastly we have our origin. Pretend this is a plan drawing and that dot is our building, so we're way zoomed out. And so our building is right here, and we can determine where the sun will be and how that will affect our building for these different times and months. Lastly, you can see here this is our latitude, and it's really important that you're using the right latitude. So ours is 36 degrees. But make sure that when you pick your chart, you have this right latitude for your location. And the last tool that we're going to need is called the timetable plot. Here's the timetable plot. This is a graphic plot of average monthly temperatures of Energy Plus weather data, and it can be accessed via Climate Consultant, which can be downloaded for free from the UCLA Energy Tools webpage. You can see I've pulled up Climate Consultant here. There's a bunch of different tools, the psychometric chart, timetable plot, sun chart, dry bulb, anything you want accessed and shown in a graphic manner. So the things that you need to know about this chart is it's all about thermal comfort. So the blue times are too cold for thermal comfort, red times are too hot for thermal comfort, and turquoise times are comfortable. Now that we have our charts, we need to transfer the average monthly temperature data from the timetable plot, which tells us whether people will be too cold, too hot, or comfortable, onto our sun path chart to know when to shade the building and when to allow sun to enter. What this means is we will transfer times that are too hot on the timetable plot and label these same times on the sun path chart. So we're going to transfer these times onto the sun path chart. It's really important to note that when we're going through this process, we're going to have two different sun path charts. One for winter, which is December through May, generally colder times, and one for summer, which is June, right here, through November. So let's get right to it, and we can see how this works. So we're going to be working with our winter sun path chart. And we're not going to be worried about anything from December up to March because it's all too cold, which means we want as much sun to come into the building as we can. But in April and May, we're going to copy these times from 10 to 2 onto the sun path chart. So we're going to say here's May, from 10 o'clock to 2 o'clock, I'm going to shade in that little block. Here's April from 10 to 2, I'm going to shade in that little block. And what this is going to do is tell us when the sun is anywhere in here, we want to make sure that we're not shading, or we attempt not to shade the building because people are already comfortable. So we're going to go through this process. This is the winter sun path chart. Now we're going to move to the summer sun path chart. So looking at the summer sun path chart from June, starting in June all the way till August, from 9 approximately, 10 o'clock for July, to 4, we're going to transfer these blue times, which people are comfortable, onto the sun path chart. So I say here's June, I'm going to look below the line, go to 9, shade in from 9 to 4, people are comfortable. Then I'm going to go to July, below the line, 10 o'clock to 4. Again, it's necessary to note for summer times we're going to be shading below the line, okay, and for winter we're going to be shading above the line, which is necessary to note because this chart is for both winter and summer months, and it's depending on how you read it. So we're right now doing the summer months. Let's move on to September where we get some heat. So we're going to shade from 8 to 10, which is comfortable, right here, and then from 10 to 3, it'll be too hot, so we'll make that in red, and then again from 3 to 5, that'll be comfortable. So we're going to go through this process until we've shaded everything that's either turquoise or red, and we're especially going to note this red area where we're going to need sun shading. Now that we have our sun path chart with corresponding comfort and overheated time shaded, we need to determine the times of the year to shade, recognizing that some spring months and some fall months have conflicting shading needs, yet the same solar geometry. So we can see this when we look at this chart. In December, which is also which is winter to spring, we don't want to shade these times because people are comfortable, and we don't want to shade anything here. But in the summer, people are too hot here. So how do I shade this portion without shading this? So the answer is usually operable shading, but just for this demo and the scope of this tutorial, we're only focused on fixed shading devices. So what we're going to do next is create what's called a shading mask. And that mask is going to be a dark, bold line over the times that we want to shade, and it's going to include a lot of this red portion. What we're going to do is we're going to overlay our blob, this blue and red blob we made, onto our solar protractor, and then we're going to draw our black bold line, which is our mask. So we know that we want to shade these times with our shading devices. And again, this is the solar shading protractor, which is going to help us determine our HSA, our VSA, and our EPA. And those are going to help us decide how big to make our different shading devices. What we're going to do next is find the HSA, the EPA, and the VSA. What these angles are going to allow us to do is to create an effective solar shading strategy for Nupumu on our campus and hopefully design it better than the architects did. So let's start with the VSA, and then we'll move forward from there. The VSA is the value used to find the shadow altitude angle for an overhang. So this, again, is going to be the angle that we look at in section. So we're deciding the size of an overhang, and these VSA angles are shown here in blue, and we're going to choose one of these blue lines, or one in between or near one, that shades the predominant portion of our mask. And again, our mask is this black bold line. So I've chosen a VSA of 55. So what I did is I looked right here and I said, okay, I want to cut off a little bit of this red here and shade that. So I've shaded that. Ideally, we could shade a little bit more of this red, but just for this tutorial, we're just going to shade this portion just because we know we have some things coming later, which will help us shade some more times. Now let's look at what this VSA actually means. So we talked about it in showing in section, and what it's going to look like is this. We've chosen a VSA of 55, so we can see that that angle 55 is the angle of the sun, which will be shaded by our device. And what we're going to do is we're going to draw an angle from the bottom of our window, again, that's from the bottom of our window. We're going to go up 55 degrees here, 55 degrees, and extend this angle line all the way past the window. The next step is we draw our overhang. Okay, we draw our overhang and we extend that line from the top of the window all the way out until it meets that angle line that we've extended. What this is essentially doing is blocking any sun that's higher angle than 55. So anything that comes from here or anything that comes from here, anything like that. And there's two different strategies to use this, or there's an infinite number, but you can use any number of overhangs. You can use 1, you can use 2, but it's necessary to note when you're using 2, you extend 1 halfway up or a third up, whatever it is, and then you extend the next one from that point on the window where that overhang starts. This is going to allow us to create an effective solar shading strategy for 55 and higher angle sun. Here you can see this is what it looks like now with sun coming in at 55 degrees and even at some smaller angles. Here we're blocking all sun angles higher than 55 degrees. The next step that we're going to go through is determining the end profile angle. So the end profile curves are these black curves hidden back here, and these go up and these help us determine the size or the width of our overhang when looking at it in elevation. So the EPA is, again, our width of the overhang, and it's depicted by these light black lines. And I've decided to use an EPA on this east side of 60 degrees and a 30-degree EP on the west side. What that's going to allow us to do is it's going to allow us to shade this portion right here. And this is key because we're not shading this morning time here when people are comfortable, and this morning time when people are even too cold. And we're also not shading this afternoon time when people are cold. So the EPA is really helpful because it allows us to manipulate the shading device to allow for some of these morning and even evening times to get sun. What this is going to look like in an elevation is it's going to be an extension of our overhang on the east and west sides. Again, this is a south-facing elevation. So we're extending our overhang to the east and west to block those angled sun from the east and west, which usually come in the morning and in the evening. So it allows us to block that high angle sun, but allow in some of that morning and afternoon sun. Again, you can see here we have our as designed window in Nipumu on the Yeki Tutu campus. And what we're going to do is we're going to use either 2 overhangs extended this way or 1 overhang. And you're doing the same thing. You're drawing your 60-degree angle, and then you're extending that line to where it will hit the overhang. On this side, it's 30 degrees. So I've chosen 2 different EPAs so you can see the difference in what a 30-degree angle EPA will look like. It's going to be longer versus a 60-degree EPA. So now that we have our overhang sketched out, we are going to move to vertical fins. To size the fins, we are going to use the HSA to determine the shadow azimuth angle required to shade low altitude sun, especially late in the day coming from the west. What this is going to look like is these red lines are our HSA lines. And these HSA lines vary anywhere from 90 all the way to 0 and then to 90, depending on which side of the window you want it on. So I've chosen an HSA of 60 degrees because I want to block some of this afternoon sun when the ground is heated up and generally people will be a little bit warmer. So I'm choosing this 60 degrees because it blocks just a little portion here, and it's going to block this right here, these times. So when I do that and I shade it, it's going to shade in these times. And the effect this is going to have, remember our HSA is understood in plan, is it's going to create this fin. And a fin is a shading device that extends from the elevation straight out and runs up the side of the window. So this is as the building is designed currently with a little fin right there, but it doesn't block any of these late afternoon sun angles. So what we've done is we've chosen our HSA of 60, where we draw our angle extending from one of the corners, depending on which side. If you choose this side, you extend it from here. If you choose one over here, you extend it from this side. We extend our angle out over, and we extend that line all the way up until it hits the fin, and that's where the fin stops. So the effect of this is blocking all this late afternoon sun from coming in. And you can see there's another option where you can create 2 vertical fins, but the downside of this is if you have a fin here, this is going to act to block 60 degrees from both the morning sun and the afternoon sun. So that's really important to note. Let's just go through a little recap. Today we've discussed VSA, EPA, and HSA. VSA here is about the sun altitude. HSA is about the azimuth more so, and it's creating these fins. And our EPA again is determining the width of the overhang. So in summary, we have created a more effective shading strategy for Nipumu. I wish they'd hired us, right? So here's a multi-view drawing of what we've designed. So this is how it's designed currently. And what we've done is we've extended this vertical fin, which you'll see on the next side. And we've changed the overhang to be a little bit longer to block that high angle sun. And we've extended the overhang to both sides of the window on the east and the west according to our EPA. Next, you can see this is according to our HSA. We've extended this fin out to block those late afternoon sun angles, especially at 60 degrees or later. So today, what we are getting from this is how to use the solar protractor, the polar sun chart, and the timetable plot. These 3 pieces of data or these graphics are used together to create effective solar shading strategies. And the other part of this tutorial should tell you how to sketch and plan section and elevation with regard to sun and sun shading devices. So you should now be able to create effective mitigation strategies using the data provided in these 3 charts and understanding plan, section, and elevation together and how they work in this process. So thanks for watching. Goodbye.